Hello and welcome back to High Peak Education. I would like to record a intuition video which shows how electromagnetic induction works. Let's look at several simulated experiments of electromagnetic induction, starting off from the historical perspective, and namely people like Michael Faraday. So imagine we have this wire wrapped around an iron core. And what we have is a DC power source with a battery, and we also have a switch. Also notice over here we have a galvanometer. Now, by the way, a galvanometer is very similar to an ammeter. It's basically going to show us a difference in electric current. But if we have in this iron core, we know that iron is a ferromagnetic material. That is, it supports significant amounts of magnetism. So we expect that when the switch is closed and current is running on this coil over here on the left, we expect that there to be a magnetic field generated here. Now here's what's interesting. Faraday realized that even though a circuit could be set up on the left, only at the moments when he first closed the switch or he first opened the switch did he observe an electric current on the secondary coil. In other words, this magnetism, this effect of changing the magnetic field seemed to affect the magnetic field and thus the current on the other coil. So let's go ahead and close the switch. Notice what happened. The current is now running, but for a brief moment, there was electric current on the other coil. Notice also that when we open the switch, the current goes the opposite direction on the other coil. In other words, there seems to be some effect of changing the magnetic field in time for the primary coil seems to affect the magnetic field and thus the current induced on the secondary coil. So now we're finally bringing in some calculus. Now we're finally bringing in changing fields with time, starting off with the magnetic field. And as we'll see, it's actually going to be the magnetic flux through these coils that really matters. Let's have a look at another experiment. So what is shown here is what we often call a bar magnet and a pickup coil. And a pickup coil is a coil of potentially several loops, but it's a coil that has a resistor attached to it, and we're going to see if we can generate any electric current on this loop. So what we're going to do is we're going to change that magnetic field, thus also changing the magnetic flux through this loop in time. So this is what Faraday's experiments seem to observe. So if we take this bar magnet and plunge it through the loop, it looks like we get an effect. In other words, we get light. We get electric current, which is lighting this light bulb. So we do it kind of slow, doesn't seem to have as much an effect. We do it much faster, it seems to have a greater effect. Now, it was proposed that this could be a generation of electricity. Notice that if we move the magnet towards or away many times, and we paid some people to do that, I mean, this stuff was discovered in the 1800s. This is before the abolition of slavery in the United States. It was calculated that the amount of electricity that they would produce was impractical. Okay? Glad we've evolved to having slavery and being outlawed now. But in either case, even if you did pay someone, notice that you would you're going to get a significant amount of electric current only if you have a very long period of time or very strong magnets, and even so, it's not very practical. So notice that only the motion that's towards or away from the coil is important. Any motion that's parallel to the plane of the coil, or you might say if this magnetic field is to the right and the area vector is to the right, any motion of the magnetic field that's perpendicular to the area vector, which would be zero flux, so zero change in flux, is not going to produce any induced electric current, but only that which is parallel or anti-parallel. Now, by the way, notice that there is some polarity here to the direction of the way the electrons move. You can kind of see that on the wire here, but let's put another voltmeter on here. So let's move it to the right. Looks like it's negative. Let's move it back to the left. Looks like it's positive, positive, negative, and so on. Okay? We may ask, what should increase the strength, the amount of induced current? Well, let's start off with the simplest thing. Notice that if we increased the strength of the bar magnet, notice that these colors are now getting darker because it's now a stronger bar magnet, and indeed we definitely do get a larger voltage being induced. Still no effect when we move parallel to the plane of the loop. By the way, if we flip the magnet polarity, we can just get effects in the opposite direction, from the south pole as opposed to the north pole. Okay? So let's flip the magnet back around. How about if we increase the number of loops? What do you think should happen? Well, there should be greater magnetic flux because we just have more loops. And notice that now with more loops in place, we should get more induction because we have the magnetic field lines are moving through a greater number of areas. We should just multiply by 3 because the integer n is just 3. Look at that. Now the induced voltage is quite a bit larger with 3 loops as opposed to one single loop. Here's one last question. What about the area? What happens if we increase the area? Let me move this down, by the way, so you can see a little better. And this too. What happens if we increase the area? Okay, it's even greater than it was before. And it's hard to see, but let's just do this for one loop. So it is larger than we had before. And the reason is because greater area, greater flux of magnetic field lines, so we should have a greater effect of this electromagnetic induction. Do not be scared of the word electromagnetic induction. Just break that word down. Electro, meaning generate electricity. Magnetic, we're using a magnet. So electromagnetic induction. So we're inducing, that is, we're creating when it was not there in the first place, electricity using a magnet, using changes in magnetic flux. Okay, so we'll now examine this from another perspective. So now what I have here is I have a metal bar attached to 2 conducting rails that it's in electrical contact. What we also have here is we have a magnetic field which is shown to be into the page. So that's what it means by these little X's. And we are going to see if a changing magnetic flux in time should also induce electric current. Now listen to me for a second. In the previous 2 examples, we changed the magnetic field as a function of time by either switching on the current or by taking the magnet and plunging it through the loop, the pickup coil. The question is, can we change the current in these conducting rails that's going through this resistor if we change the magnetic flux through this area formed by the wire, the rails, and the bar? And that's going to prove to be a change in magnetic flux, not just a change in magnetic field overall. By the way, we can adjust the resistance in this resistor, the magnetic field strength, the applied force initially to pull on this bar, and we'll see what the terminal speed of this bar is. We'll see what the EMF generated was, and so on. Now, by the way, one more thing is that we'll also be able to see the current and the time this takes. Here's the mass of the bar and the length of the bar. And one thing to note is that let's assume that these rails are frictionless. So that is to say, anytime the bar would slow down or stop accelerating, it turns out that's only going to occur due to the fact that there's a magnetic force in the bar. Because initially we're going to pull this bar with an applied force. Okay? Now, by the way, if this thing reaches a constant or a terminal velocity, the applied force and the magnetic force should roughly be the same in terms of magnitude. But let's go ahead and see what happens here. So we're going to apply this force on this bar. It's going to slide on these rails, stay in electrical contact, and let's see what we get in terms of current and induction in terms of the EMF. So let's go ahead and start. So look at that. Notice that over time, over a short period of time, we yanked the bar and the magnetic force built up, and then we got to a constant terminal velocity. Now let's reset. So notice that the magnetic force starts off at 0, but then the faster we go, the greater the velocity is, and the faster we go, the larger the electromagnetic induction, because we have a larger changing magnetic flux in time. That is, the number of X's in this area of this circuit, and I mean actual electric circuit here, not just continuous rectangular loop. But in this circuit, the number of X's, which are penetrating through that conducting circuit, are increasing in time. So the faster we go, the more electromagnetic induction we have, the greater the change in the magnetic flux with time. So the greater the current should be induced, and then also the current in there should produce for us a magnetic force in the opposite direction. And let's think about why that is. If the electric current is up and the magnetic field is into the page, the thumb should point to the left. That's the direction of the magnetic force by the right-hand rule. Let's watch it one more time. Notice that there's a certain amount of input power, which is based upon force times velocity. Notice that ended up being the same electrical power dissipated in the resistor. Because if we assume these conducting rails are resistance-free, then this resistor dissipates that power as light, heat, or whatever form that resistor takes. Notice that the direction of the current is upward. Now, how do we actually know that? Well, imagine when you yank this bar. When you yank the bar, the electromagnetic induction increases because the magnetic flux is also increasing. Now notice, you could hopefully imagine from Newton's third law that there should be some response effect from this force trying to pull the bar out. In other words, there's a magnetic force to the left. Now, why is that the case? Well, imagine that this flux is increasing. That is the magnetic flux. I would say that this circuit, again, this circuit means an electrical circuit and a continuous rectangular loop. But this circuit should induce its own magnetism. In other words, its own magnetic flux, which tends to resist the change of the changing magnetic flux. In other words, as the areal extent, that is the size of the area in the circuit, increases, we have greater magnetic flux that's into the page. We're going to have current generated by the bar and by this circuit that tends to resist that change. So in fact, if the current in the bar is upward, then the current is running in the counterclockwise direction. So if we wrap our fingers using right-hand rule 3 in the direction that the current moves, sorry, this is actually right-hand rule 2, but if we wrap our fingers in the direction that the current moves, the thumb points out of the page. So the thumb pointing out of the page is the opposite direction of the magnetic field that's shown to be into the page. So, in other words, the current that's induced tends to resist the change of the changing magnetic flux. Now, by the way, that resisting of the change is a minus sign in Faraday's law. So even though Faraday is the one that kind of came up with the law, Lenz's law tells us about the direction of the induced current. It tends to resist the change. In other words, you never really get energy for free. And every action force, there's sort of this equal and opposite reaction force by Newton's third law. So, let's try this example now with a larger resistor. So the resistor now is about twice as much. Okay, so let's see what happens when we do the same applied force. Notice that there's more input power and there's greater electrical power to the resistor. Because we have a larger resistance, the current does not build up as quickly, so we have to input more power before we get to terminal speed. Notice the terminal speed is actually larger than it was before. Remember before, when the resistance was 6 ohms, the terminal speed was only 1.145 meters per second, and the induced voltage was not as much. Okay? Now, let's now keep the resistance constant, and let's increase the magnetic field. Well, I think that since there's a larger magnetic field, we'll build up that magnetic force more quickly. So yeah, the terminal speed won't be as much. So look at that. With just a small tug, we get a huge magnetic force very suddenly, and the terminal speed is very small. There's a very small induced EMF also, because the magnetic field is so strong, so it didn't take much velocity to get such a rapid change in the magnetic flux. Let's make another change. Let's have a much larger input applied force. Well, if we double that input force, I think the terminal speed will be greater, and it's going to take longer to reach its terminal speed. Let's see that. Okay, so that is indeed the case. Because if we pull with a larger input force, there's more input power than the original experiment required, and more power dissipated to the resistor. So we have to generate current over a longer period of time, generating a larger EMF, thus finally getting us to that terminal speed, where the sum of the forces in the horizontal direction are 0. And that's because we are getting to equilibrium by Newton's second law. Okay, so let's try to imagine what's going to take the longest time to build up this to a terminal speed. So if we have the largest force, that should increase the terminal speed. I would also say the greater resistance. Why greater resistance? If you have a greater resistance, you should have, it's more difficult to build up the electric current, so it's harder to produce that induction. And then how about the magnetic field? Well, if it's a large magnetic field, it builds up flux quickly, so let's build up this flux slowly. Okay? So let's build up a very small magnetic field. Now, by the way, they may look like dots to you, but those are actually very, very, very small x's. So notice the terminal speed here will be 17.316 meters per second. So let's start this. Okay? So it takes a really long time to build up this current and build up this induction. So we need to put a lot of power in to get this to its terminal speed. Okay? So probably too much for the simulation here. So let's put the magnetic field back at 6 Teslas. Okay, so it definitely takes a lot of electrical power when you have a large force and a large resistance, but I mean, it's still manageable. Remember, 10 ohms is a modest resistance, 6 Teslas is a huge magnetic field, and then 0.1 newtons is a modest force. Notice that these are reasonable values. 100 grams, which is 0.1 kilograms. Length of the bar is 24 centimeters, so 0.240 meters. So anyway, these are very reasonable numbers, which this could possibly be done in a laboratory experiment. By the way, again, these rails assume to be frictionless. This is still sort of ideal. In reality, we can't get rid of all friction. Okay. Let's have a look at another example of electromagnetic induction, now that we understand Faraday's law and Lenz's law better. Now, what I have shown here is what I'm going to call an electric transformer. What is an electric transformer? Well, the word transformer means that we can transform the voltage and also the current to a different value using electromagnetic induction. In fact, we can transform that voltage using Faraday's law. So what I have shown here is a DC power source. Again, direct current, something like a battery, and we have some coils. Now, by the way, we assume that there's some resistance in this battery. Otherwise, we'd have a fire, we'd have infinite current, which let's assume there's some real resistance here. Notice, suppose we want to change the voltage to a different voltage. Now, you could think about lots of situations where you might want this. You're going from a power source to another power source, and you want to change the amount of voltage. And let's say you want to change it through air, okay, without necessarily having the objects touching. Well, that can be accomplished through a changing magnetic flux through this area. The changing magnetic flux through this area is going to come from the fact that we can change the flux through the ways we've discussed before. So we can move this towards or away, and we see some effect of there being an induced current. We could imagine increasing the area. Now, by the way, if you increase the area of these loops, notice you have to look very closely here. I'll move this closer. But you do get some effect of changing the area does change the magnetic flux, but in practice, that doesn't work very well. So what we instead do is the following. We either want to change the orientation of these loops, but that's also impractical if we're going to install these, let's say, on power lines or something. So we can't change the orientation of these areas. So instead of having a DC power source, what if this power source is time variant? So let me change the voltage from a positive polarity on the right to a positive polarity on the left, and then back and forth. Notice I'm changing the polarity here, and especially if I change it quickly, I am getting an effect right here. Now let's move these closer to each other, and let's see if I can get a larger effect, because again, this is a magnetic field, so the distance away really matters. So yeah, we are getting a substantial effect from changing the magnetic field. Now again, we're not going to pay slaves to do this, and that's illegal. What we're going to do instead is, instead of having a DC power source that's direct current, we're going to have an AC power source, which is alternating current. Now look at this. We have alternating current. Let me show some modest values at first. Okay. So here we have a modest value of amplitude and a modest value of frequency. The amplitude is shown to be about 50% of what it can do maximally, and the frequency is shown to be about 51% of maximal frequency. Notice if we increase the frequency, the current is changing more often, and we are getting greater voltage here. A little hard to see, but let's go ahead and switch back to that 51%. Okay, so that 51% is not as much of a voltage induced on the secondary coil. By the way, we often call this the primary coil and the secondary coil. So this is 1, this is 2. Okay? So notice that if the frequency is higher, indeed the voltage you induce is higher. And you can see that if you move closer, but if you reduce that frequency, notice that it's not as high. Okay? Now, by the way, the frequency is set by the governing authority. So in the United States, I've mentioned before that the frequency is 60 hertz. In Europe, the frequency is about 50 hertz for the alternating current frequency. Now, depending upon what country in the world you're in, you're going to have to look it up for your standard. Okay, now let's move on and let's say, what happens if we increase the magnitude of the current from the primary coil? Well, if we increase the magnitude of the current and the voltage, indeed there is greater voltage on the secondary coil. What if we are going to increase the number of loops? Notice that if we increase the number of loops, there's also a greater effect. Because again, there's greater change in the magnetic flux here, and thus there's greater change in the magnetic flux on the secondary coil. Okay? So it turns out that the number of turns, which is the same thing as the number of loops or the number of coils, really has a strong effect on these transformers. In fact, if you double the number of coils, you should double the induced EMF. Okay, by the way, just to prove to you, let me put a compass in here. So notice that you can see very clearly that the compass changes its direction. And then again, the compass change in the direction is a reflection of alternating current in a AC electromagnet producing alternating current that goes the opposite direction and has a different voltage on the secondary current. So this is what we mean by an electric transformer. Now, by the way, part of the reason these are so important is because electrical transmission on electrical grids is usually done at very high voltage. So if we go with a step-down transformer, we step down from high number of turns to a low number of turns. So the voltage here is quite a bit smaller than the voltage in the primary. But that's good because if we transmit power, electrical power, at high voltage, we want to step down the voltage to more modest values when we actually get into a commercial or residential area. But if the power is conserved, now power being conserved is like energy being conserved, but it's just energy per unit time. If the power is conserved, the primary, that is the high voltage transformer, will have generally low current. But the secondary, which is a smaller number of turns, smaller voltage, will have much higher current because we know power goes like current times voltage. So if the voltage goes down, that's a step-down transformer, the current actually goes up. Okay, so I hope that makes sense about what an electric transformer is. Now, here's the other thing that I want to mention about why AC is so important. Alternating current is not only useful for transformers, it's also often generated by electric generators. And let's see the reason why that is coming up here in a moment. So what I would like to talk to you about now is 3 versions of an electric generator, all having the same core principle. Now, an electric generator is going to be the following. Mechanical energy is the input, and electrical energy is the output. Now, that's different from an electric motor. Remember, an electric motor had electrical energy as the input and mechanical energy as the output. So in some sense, it's almost sort of the reverse of an electric motor. Now, notice what we have here is we have a very strong magnet, and we have a conducting loop, and we have these brushes, or these slip rings, and it's, again, this is sometimes called a commutator. Notice the output that's on this light bulb is alternating current. Why alternating current? Well, let's have a look at the magnetic forces. Look at these magnetic forces. Imagine someone on the other side is turning a crank to have this loop rotate. Now, by the way, in practice, it's not usually a person sitting there turning a crank. Usually there's some sort of a gear, and usually that came from some sort of a crankshaft, and that crankshaft in the first place is probably turned by a boiler. What do I mean by a boiler? Well, typically we're going to boil water, and we're going to get the water to very high temperatures, and that's going to move a piston, and that piston's going to move that crankshaft and then turn this coil. Okay? So the idea is that, how do we get water to a high temperature? Well, this is what we do in our electric power stations. A lot of times we get water to a very high temperature by burning fossil fuels. That's the traditional way. So burning things like coal, natural gas, and so on. Of course, that affects the environment. So there's a movement away from burning fossil fuels. So what's another way to do this? Well, we could have a nuclear reaction. A nuclear reaction occurs at a very high temperature. And again, we get the temperature of the water in that boiler under high pressure to a very, very high temperature. And again, that can run our boiler and run our crankshaft and so on. Another way this is often done is, let's say, through wind power. You can imagine a wind turbine rotates, and as long as you change the gear ratio in what's called the gearbox, you can rotate this coil through a strong magnet at the rate that you want and at the frequency that you want, and you can generate electric power. Okay? So again, in the United States, we should be generating electric power at about 60 hertz. But we want to generate as much electric power as possible. So as the turbine turns, especially if it's very windy, it's producing a lot of electric power. So notice what's going on here. Why are the magnetic forces like we see? Well, notice that the magnetic forces on the ends of the loop are basically either zero or towards one another. In fact, let me stop it right about here. Right about there. Notice that the only reason this loop continues to rotate is because it has inertia from the fact that the person is inputting mechanical energy. And again, it's not usually a person. I mean, on a crank flashlight, maybe you've used a crank flashlight before, the input is the mechanical energy of a person. But again, a lot of times in practice, it's more like, an actual piston turning a crankshaft, turning a loop. Okay? But the idea is that, notice that these forces are towards one another. Why is that? Well, we have a magnetic field here, and we have current going through this loop right now. Okay? So in fact, the current should be moving through, and we're about to change direction of the current due to these slip rings. Now when the current changes direction, say let's stop it right there, let's think about what's going on. So notice that the magnetic field is from south to north, and then we also know that if the current is in a certain direction, say on the bottom of the loop, we should get a magnetic force that's in a certain direction. Well, if the magnetic field is south to north, then the current, that is the conventional current, the positive current, should be moving this way, and up here it should be moving this way. Now on the top, we would do current this way across the direction of the magnetic field, and the thumb would point that way. Notice that the direction of these magnetic forces is to resist the change produced by the crankshaft. Because left to its own devices, if the crankshaft suddenly shut off, I think this loop would tumble back counterclockwise from our viewpoint, from the viewpoint of the light bulb. But we note that this thing is not turning counterclockwise from the viewpoint of the light bulb. It's actually turning clockwise from the viewpoint of the light bulb. So there has to be some mechanical input. That mechanical input works against those magnetic forces. Again, because of Lenz's law, those magnetic forces resist the change. That is, they resist the electromagnetic induction, which is the changing magnetic flux. Now, by the way, if you've ever actually cranked a hand crank flashlight, you'll notice the more you crank it, the harder it is to crank it. Because when you build up a lot of current, and thus the flashlight bulb is bright, you'll notice that, there's a lot of electromagnetic induction you're working against, and Lenz's law is at play, and also is Faraday's law. Notice that, suppose we were to increase the rotational speed. Hopefully you'd expect this light bulb is brighter because the magnitude of the current is greater, because if we turn this faster, we're working against the magnetic forces stronger, and so we have the magnetic flux is changing more rapidly in time, and by Faraday's law, that gives us a larger voltage and also a larger AC current. Notice the output is AC, alternating current. Hence why alternating current is so prevalent and useful on electrical grids. So this is a stripped down, or sort of a very simple version of a electric generator. Let's look at two slightly different versions. Now what I have here is a different version of an electric generator. We're going to generate electricity on this coil. What is shown here is water from a pipe or a spigot that we can change the flow rate of, that is the volume per time. We also have a compass, and this compass is going to show us the direction of the magnetic field. Now, as I've said before, in order to generate electricity, in practice, it does not make sense to change the area of the loop, nor to move the magnet in or out. But one of the things I hope you realized looking at that last electric generator is if we change the orientation of the loop, that is, we change the direction the area vector points, we can produce electricity in an electric generator. Now, by the way, now let's change the orientation of the magnet compared to the loop. So now let's keep the loop constant, but notice it's all about relative motion here. Whether the magnet's turning over and the loop's staying put, or the loop's turning over, which in practice is a lot more common, and then the magnet usually stays put in most modern real electric generators. But let's see what happens when we turn on this water and we start having this loop rotating. Notice we're generating some electric current. Notice these electrons are moving back and forth via AC every half turn. Look at this compass. This compass is being attracted. Let me pause it here. Notice that the south end of the compass is attracted toward the north end of the magnet. And then another half turn later, the north end of the compass is attracted toward the south end of the magnet. Notice when the bar magnet points toward, when the bar magnet points toward the loop, that's different than when the bar magnet's perpendicular to the loop. So it turns out that there's some fluctuation here given the rate at which the magnetic field is changing in time. Let's also see what else we can change. Let's first, instead of just a light bulb here, because now we know electricity is present, let's put a voltmeter. So now we actually see the polarity, positive and negative. Let's think of some ways in which we can increase the voltage being produced. So first of all, let's increase the number of loops. So if we increase the number of loops, we do get greater voltage because we have greater magnetic flux through the coils if we have more loops. So in practice, there are thousands of loops on modern electric generators. Next, let's see what happens if we increase the area of this loop. Okay, not a huge difference, but there's some change. Okay, and then now, let's suppose the bar magnet is stronger. So if you don't believe me, by the way, let me pause this and show you the field strength, and let me increase the strength of the magnetic field. Okay, so you see the colors are getting darker, and that's because we have a stronger magnetic field. So now let's play. Okay, now we have a stronger magnet. We have greater induction of AC current. And lastly, what if we increase the flow rate? Well, if we increase the flow rate, we'll increase the frequency of the rotation of this paddle wheel, and thus we'll increase it to a greater frequency of AC, but that's okay because as long as we're changing the electromagnetic induction more rapidly with time, then we should have greater induced electric current. So let's in fact do that. So now when this goes faster, indeed, look at that, 100 RPMs, 100 revolutions per minute. Look, we're getting a really large voltage now. And you can see the light bulb is extremely bright. Okay? Now, by the way, you may ask, why is it that I don't see light bulbs blinking all the time? Well, in some sense, they are. In some sense, there's some inertia of heat from one to the next. Okay? But keep in mind, even though this is happening 100 times per minute, suppose I backed off to 60 times per minute. Well, that would just be 1 hertz, because 1 hertz would be 1 time per second. Remember, in the United States, this is occurring at 60 times 60, so 3,600 RPMs, or 60 times per second. So the light bulb is blinking so fast you barely ever really see it. Now, by the way, this leads to some interesting results. When you're in Europe, and I mean, I've been over to Copenhagen and to Paris and various other European cities like Milan and Venice. If you look at a white television screen over in Europe, it looks like the television screen is blinking very slow. Why is that? Because my eyes are used to 60 hertz. My eyes are used to looking at white television screens that are blinking 60 times per second. Whereas in Europe, they blink a little bit slower. They blink at 5/6, so they blink, about 10 or 15% slower. As a result, it's just very weird for our brains. We kind of have to get used to it when we're looking at certain lights or, say, television screens or whatever when we're not in our home country. So just keep that in mind, right? This is an artifact of the fact that we have alternating current generating our electricity. So don't let it wig you out. By the way, when fluorescent bulbs get to be near the end of their life cycle, usually a lot of times you will see them blink. Okay? So again, that's reflective of the AC current. Let's look at one more example of a generator, and this time let's be even a little more quantitative. So for our final experiment of electric generators, let's go ahead and look at an electric generator in which we can change the rotation speed. We can also change the magnetic field strength. Okay? And we can watch the induced EMF. Now remember, the induced EMF is a voltage. Remember, I don't even want to mention what the EMF abbreviation is for, because it's really an archaic 1800s term. But we're going to see this light bulb light up with alternating current. Now notice we have much more realistic looking slip rings here. You'll notice that the electrical connection again is going to flip over every half turn. Okay? So we'll start off at 200 RPMs with a strong magnetic field of 5 Teslas. Notice this is what alternating current looks like. Look at the direction of the electric current here. It changes direction every half turn. If you plot the voltage induced as a function of time, it's like either a sine wave or a cosine wave. The only difference between a sine wave and a cosine wave here in practice is that do you start at 0 or do you start at the maximum value? That's sine versus cosine when you're studying this electric generator. That just depends upon how you want to set your time equal to 0 point. Well, notice these slip rings. Look closely on these slip rings. Do you see that this armature here has points of contact, which again, every half turn changes the polarity. Okay? So we've got something rotating this here. So who knows what the input is here? Maybe this bar goes back to, again, a crankshaft, and I already explained all that before. So now, let's change this to, instead of 200 RPMs, let's go 400 RPMs. Now notice, look at this. It seems like we're getting twice as much of an EMF. So I think the bulb should be brighter, and indeed it is. Because, notice the frequency is greater, so the spacing between subsequent oscillations is smaller, because we're plotting voltage versus time. Also note that in the animation, this is turning over faster, and the bulb is blinking more often. Now, what if we increased the magnetic field strength? By the way, this is why there's such a market at times for these rare earth magnets. Rare earth magnets are not necessarily made of iron, because iron can be magnetized, but it's not always a really strong magnet. There are other elements out there that can sometimes produce very, very strong magnets. Gadolinium is one example. But let's just assume we have a very strong magnetic field. So look at that. If we've doubled the magnetic field, we should double the voltage. I think it seems to make sense because we're doubling the electromagnetic induction. So now, even though the frequency is as it was before, the bulb is brighter because now we have larger magnitude of voltage induced compared to the original experiment. Okay, lastly, what if we do both? What if we have a stronger magnet and we have greater, that is more rapid rotation speed, in other words, a greater frequency? And I know you're on the edge of your seat by the end of this video, but it's definitely going to be a large frequency and a large amplitude, and we're now generating a large amount of AC voltage and thus also AC current. So this is basically how electric generators work. Now we finally understand Faraday's law, Lenz's law, electromagnetic induction, and even its applications to transformers and also electric generators. Thank you very much for watching this video, and thank you for your attention. Please smash that like button if you enjoy this content. Please share this video amongst your social network and subscribe to the channel in order to grow the channel. I want to thank you for watching High Peak Education, and I will see you in the next video.